Thank you very much for the introduction. It's a pleasure to be here. Like most of you, I may not have known exactly what we were getting into when we were coming. But I'm going to give you a talk today which, under my understanding of this meeting, to try and reach out to see what other types of collaborations might be available among our sister institutions within the SEC. And in order to do that, I'm going to first talk about my home, as in the University of Alabama and my research group. I'll talk to you a little bit about ionic liquids and our biomass strategies. And while I'm doing this, I'm going to talk to you about our motivation and our direction for how we are approaching the things that we do. It might serve as a bit of a counterpoint to some of the things that we've been hearing throughout the week. I think there are maybe some contrasting and different views on how best to move forward in the areas of renewable energy and chemicals. But hopefully there's room for a broad number of different perspectives to try and help us move forward. If you haven't been keeping track of the University of Alabama, except on the football field, then you may not realize that we have grown over the last 8 years to now over 33,000 students. This has been a tremendous growth on campus. And of course, most people are interested in the football trophies that we've been getting, and I was required to put this picture in my presentation by the university. But I want to point out something here called Shelby Hall, right at the top. In 2005, this pentagonal building, for obvious reasons, was the new chemistry and engineering complex. It's called Shelby Hall. A couple of years later, a second building, the science and engineering complex, was put in. But these pictures are so changing so rapidly. I want to draw your attention to this region and where this Shelby Quad is right now, because if you go to campus today, there's in fact another building and a fourth one that's currently under construction. I have to say that I've never seen facilities for science and engineering grow so fast or so well at any institution. It's certainly one of the things that we would invite all of you to be able to come and see and share with us. I'm also the director of the Center for Green Manufacturing. We started this before green was a politically correct word, but it still was meant for the same purpose, to bring scientists, engineers, and business people together to develop new green and sustainable technologies. About 5 or 6 years ago, we added an entrepreneurship component to that, and Dr. Dan Daly is currently the director of Alabama's Innovation Mentoring and Entrepreneurship Center. And I think from the talks that we've seen at this meeting, all of these things are going to be necessary to drive new technology in the future. One of the things we've done is that we've also started our own startup company, 525 Solutions. It is being run by PhD graduates from the University of Alabama, so we are trying to create jobs in Tuscaloosa for people. And this company is being incubated on the University of Alabama campus to be able to do the next stage development of new technologies that we might develop. So the products that we're trying to produce are entrepreneurs, new technologies, new companies, and new knowledge. And most of you are academics. You understand how hard it is for me to stand up here and start with entrepreneurs instead of new knowledge. I only do it to shock most of my academic colleagues. They're all important. But I think that for a long time we have not put enough emphasis in taking the technologies and getting them out into the marketplace while teaching our students to be able to take them themselves as they develop. This is my group at the University of Alabama. Currently we have quite a few graduate students, undergraduates, and postdocs and staff scientists working together with exchange visitors. We work very closely with the Office of Technology Transfer, directed by Dr. Richard Swatlowski, and AIM, directed by Dan Daly. And the funding typically comes from a mix of federal agencies, the startup companies, and also larger, more well-established companies as well. All right, so that's a little bit about the University of Alabama, except maybe for my colleagues from Mississippi State. Maybe no one knows about ionic liquids. I'm only going to mention these in the context of what they are so that you understand we're trying to take something new, which we believe is new, and to utilize them in new ways. So I will not show you necessarily a lot of structures, But an ionic liquid is quite simply a liquid salt, a salt which is liquid at room temperature or below. Some people will say 100 degrees. But if you can imagine just something that simple, the idea of a salt which is liquid at room temperature has generated something like 30 to 40,000 publications over the last 15 years and probably 10,000 patents and patent applications, because it's really changed the way that we think. One of the areas that it started in was the area of green and sustainable chemistry, because ionic liquids, liquid salts, these are not solutions, these are pure compounds, can behave just like normal solvents like water. They can be totally non-flammable, which means you could use them in applications where flammable solvents would not be appropriate. And indeed, you can have liquid salts which are immiscible with water, which is where we actually got started in doing separations with these things. But today, and I won't give you the 3 other seminars on these topics, we're making rocket propellants, we're making new pharmaceuticals, others around the world are making new liquid crystal displays and the like, and the technology into batteries and electrolytes and many of the energy fields just keep going on and on. All right, I have not heard much about green chemistry at this meeting. I did hear a little bit in the plenary and keynote areas, but I will point out that this theme, which is trying to design chemical products and processes that reduce or eliminate the use and or generation of hazardous substances, is going throughout all of the things that we've heard, especially in the energy field. Sometimes I think that it's forgotten. You may have heard me ask a question of one of the plenary speakers at the beginning, because this idea of environmental integrity is more than just unit efficiency. It's watching out for climate change, minimizing damage, making sure we keep biodiversity. The social aspect is often forgotten. These technologies have to have an economic impact where people have jobs. And then a lot of people forget the bottom one, economic viability. I would argue that unless we want to be like Denmark and raise taxes to 50–60% for everybody, raise fuel taxes and everything else to pay for the new technologies, then we're going to have to think about things differently. I heard talks at this meeting that indicated that we needed to hope that the government kept mandates for biofuels in place. To tell you the truth, as a chemist, as an entrepreneur, as somebody who wants to innovate something, I would rather develop a new technology that required no government support and people bought it because it was better and it cost less. And so I've tried to redefine for my students what green chemistry is about. I think green chemistry, the principles are fine, but you have to do it in a way that works and is economically viable. And if you do that, there will be new business opportunities to be had. They may not be all of them, but there will be new business opportunities simply because they make money, not because the government is supporting it, not because the taxes have been raised to make everything else more expensive. This is the goal that I think that we should have. Now, if we look at the current biorefinery cycle, I am, as a chemist, a bit confused, because we are going to take nature's most abundant and beautiful polymer, cellulose, and we're going to chop it up into something that we can burn in our cars. And for those of you that don't know much about Southern history, I was raised in Alabama. We've been making ethanol out of corn and cellulose for a long, long time, and we have a much better use for it than burning it in the car. The question that I have is, instead of trying to replace the fuels and the chemicals that are feedstocks that people know how to use today, why not replace the function of those with new materials themselves that will replace the old materials? Much harder to do, but in the long run, that's where I think that we should go. Here's what I consider to be the major challenge, and my colleagues from Tennessee have also mentioned this as well. You have a huge amount of lignocellulosic biomass, and a lot of people only want this fraction of the cellulose, and they forget about the hemicellulose and the lignin. Well, there are covalent linkages between these two that make it quite difficult to get to the cellulose. So I said I was going to talk about ionic liquids. Why are they relevant to this at all? Well, in about 2000 or so, we discovered that one of these liquid salts, I have the structure of it right here, directly dissolves cellulose at room temperature or elevated temperature without degradation. You put the polymer in, you get the polymer out. This is pure cellulose, by the way. And if you want to coagulate or recover the cellulose from this material, you simply put it in water, which acts as an anti-solvent, and you can recover the cellulose in any form that you would like. In doing this, at the same time, you can add functionality. You can control the form of the cellulose. You can make fibers, beads, membranes. You can make plastics by putting binders in. You can make a variety of new materials that can replace the current plastics and other materials that are made from oil-based products. I think that's a better use for cellulose. I think we can also find similar uses for lignin and the hemicelluloses, but even if we can't, we can use those directly as feedstocks. But again, it comes back to this challenge. Again, being from Alabama, we have a history with this type of separation. You've heard it mentioned a few times during the talk today, and that's kraft pulping. I went to school in Tuscaloosa, and I still remember what my clothes smelled like on the days when there was an inversion and the paper mill smoke just was seeped into all of your clothes. Most of those have actually closed, but this kraft pulping process, energy intensive, chemically intensive, is still used to obtain a lot of the cellulose pulp. Our colleagues from Tennessee talked a little bit about organosolve pulping. So anything that we do is going to have to compete with a cheap, dirty process. And therein lies the problem. Just to give you a little overview on how I'm going to define our results, this is lignin content on the y-axis, pulp yield. This is sort of a traditional way of measuring how the kraft process did. And if you look in the literature, you find results somewhere in this green box. So somewhere around 50% pulp yield, so 50% of your tree is recovered with anywhere from 10 to 20% lignin. And then, of course, you have to bleach it and get rid of the lignin. Now, let me give you one difference between what I'm going to talk about and this traditional process. In the traditional process, cellulose is never dissolved. Lignin is destroyed. So you're already cutting down and destroying one of your key components if you do the kraft process. What we have tried to do, since we can dissolve cellulose, and we have found we can dissolve lignin, and we can dissolve hemicellulose, in 2006 or 7, we demonstrated that ionic liquids can dissolve trees. Now, not directly, but you grind them up a little bit, and you can dissolve trees, and you can get a pretty good delignification. In 2009, we tried to do a quantitative study, and then we found in one pass, using an ionic liquid with pine powder, we like pine trees in Alabama, we were able to take wood chips from a local mill in Moundville, grind them slightly, add a liquid salt, and create a solution from which we recovered a cellulose-rich material and a new type of lignin, new type in being non-kraft lignin, directly from the dissolution. In this one process, in one pass, we got a result on this pulp lignin yield which was not quite far off from kraft pulping. Not good enough, but it was the first pass, and we decided we'd use a little bit of our chemistry, and we looked at some work that Craig Hill had done down the road at Emory in developing polyoxometylates to delignify wood. Now, Craig wanted to use these to destroy lignin. Again, we're not interested in destroying the lignin, but we are interested in breaking some of these lignin carbohydrate bonds. And so we used it sparingly, and we found that by using essentially the same polyoxometylates that Craig was using, we could now direct our results all over to anywhere that we wanted to on this map. This is the original result with pine and the ionic liquid with nothing, and then just by adding small amounts of different types of palm and changing the conditions, we were able to essentially control where we were. we still need to define the lignin and co-products which are being developed. But we wanted to go one step further because we thought that it was a little bit energy intensive, and you've heard about the glass transition of lignin at this meeting. We decided we would simply raise the temperature of this process above the glass transition, and we found that we could improve the results from 16 hours down to 30 minutes and get a better result. So there's a lot of room for optimization here in developing consistent feedstocks. That led us actually to win a small business innovation grant from the DOE to try and develop a mini reactor that would go into the field wherever you wanted and develop these 3 feedstocks. Now what happened? Well, the same type of discussion in phase 2 that we've had throughout this entire meeting. Is it going to be economically feasible? Is the business plan suitable? Is the government going to continue to insist on certain mandates? And in the bottom line, what they decided is that the process would be too expensive. Ignoring the fact that we don't have economy of scale yet, none of this has really been implemented. So we had to search around. We could either stop and say this is never going to be economically viable, or we have to find a way to succeed. What we thought is we could find a way to succeed if we could find an initial product that would pay for this process optimization and the scale up. That product also comes from Alabama, and it's called chitin. If you're not familiar with chitin, chitin is the second most abundant natural biopolymer, and we get it from shrimp shells. Chitin is actually it's a cheap commodity right now, but in its higher end applications in the medical industry, it can bring in $60,000 a gram for fibers for medical sutures. But those fibers are hard to make because of the traditional processing methods. But if you look at the structure of chitin and you think about it, it actually looks a lot like cellulose. And we decided that we should be able to extract chitin directly from shrimp shells and possibly get a product that nobody else has. Now I know y'all have seen Forrest Gump, right? That's probably, this is Forrest right here. He kind of got us on the map with Biorefinery. Do you know in Biorefinery they pay hundreds of thousands of dollars a year to landfill the shrimp shell hull waste? Can you imagine that? That's a drain on the economy. So they built a $5 to $10 million drying facility, and they were just hoping they'd take their shells, they'd be able to spread them on the field, they'd be able to use them for fertilizer and maybe at least not have to pay that result. Well, it turns out that we can take the material from their drying facility, we can extract a product which I've tried to tell them, you may not believe me, they certainly don't, that the chitin product that comes from the shells will ultimately be much more valuable than the food from the shrimp that they sell. That's where this can go. We currently have a grant from the Alabama Innovation Fund administered by the Department of Commerce to look at developing these products. In case you're not familiar with it, chitin extraction is almost as bad as kraft pulping. We're talking about energy. These are old energy and chemical intensive processes for chitin today, and there's no one in the U.S. that does this. I just read that Louisiana is going to start a facility near New Orleans, but right now no one in the U.S. does this. You take the shrimp shells, you demineralize them, look at that, and then once you demineralize them, you take the proteins out, and then if you want to use it for food or medical, you have to further purify it using methane sulfonic acid. Well, each step degrades the chitin and makes the molecular weight smaller and smaller. What we've found is that we can shortcut that process. We can take the shell in one step in a continuous process. We can extract a higher molecular weight, higher purity chitin than anybody's ever had because they've never had ionic liquids to be able to try to do it. To us, it's a rather simple process, and it looks just like dissolving trees. You start with the ground shrimp shell, dissolve it, and extract it. You can then pour water on it as the anti-solvent, and you get a new product, a chitin that is not available from any other process. One of our examples of its use is actually funded by a program we heard about on when was it, Sunday morning, where our DOE speaker talked about mining uranium from the ocean. They're planning to use a polymer, a synthetic polymer, and we said we should use a sea polymer, something that came from the sea, can go back into the sea, can be used to extract the uranium. Now, something our speaker implied, but maybe should be emphasized again, can you imagine the reduction in energy demand and environmental demand if we eliminated mining, all types of mining? If we eliminated terrestrial mining, well, let's just say we eliminated terrestrial mining of uranium. You can't imagine. I've tried to look at the numbers. They're huge. We would eliminate so much energy use, so much waste, so much land usage as well. Our strategy is actually pretty simple. We take the waste shrimp shell, we dissolve it, we electrospin a high surface area nanofiber mat of chitin, put on an extractant that is uniquely selective to uranium, and we've shown this in the laboratory. The next step is to show that this is possible in the ocean. Now, that's not all. If you think about chitin products and nobody else has had the chitin before, it turns out to be very easy to pull a chitin fiber if you have a high enough molecular weight, which is what we do. We have trouble pulling fibers from commercial chitin because it's too small. But the chitin that we extract directly from the shrimp shells works great. And because of that, we can make new products. For example, chitin and alginate can be combined into a single fiber that could be used in bandages to accelerate wound care. Now we're talking about products which have a high enough return to help develop the entire process. And because of that, 525 Solutions won a National Science Foundation Phase 1 and Phase 1B grant to study the making and use of these fibers. Biological tests have shown that they actually work, that they work better than any fibers that are known now in accelerating wound healing. We hope that the Phase 2 proposal, which is in right now, will understand that we now have a better economic proposal in making these materials. This can make money. If this makes money, it will support the development of the entire process, which we will eventually come back and use in the lignocellulosic biorefinery after it has been optimized and the investment has been put in to make it viable. That sometimes is the roundabout approach that we're going to have to use in order to develop some of the new green technologies. This is my standard advertising slide for the field. Ionic liquids have been transformational for me because they've changed the way that I think about attacking problems. They've allowed me to try to solve problems in ways that other people have given up on because they did not have what ionic liquids can do and how they work. So the fields that we are trying to move into are actually quite broad. I know you can't read this. It's just meant to be an overview of many, many different areas. We are making pharmaceuticals, and I have a whole group that is developing pure liquid active pharmaceutical ingredients that the pharma industry has never utilized before. We are making and working with new biomaterials, and mostly I've talked to you about this effort. We have a whole team in actinide chemistry in general, not just the uranium extraction. And ionic liquids are proving to be very interesting phases for actinide separations, which are important in the thorium fuel cycle, as well as the uranium fuel cycle. And we have had a project for several years with the Air Force trying to develop, for example, hydrazine replacements that are non-volatile and non-toxic. I'm actually excited to have had the opportunity to come to this meeting and to meet many of the different people from our sister institutions. One of the things that the meeting has done, and I think will continue to do, is to allow us to think broadly on solving some of the problems and bringing other ways of thinking into the equation as we go forward. Thank you very much for your attention. I feel like a movie star with all these lights up here.
Questions? So you mentioned after you do the fractionation or the dissolving that you add water as an anti-solvent to precipitate the cellulose out. What is the recovery on your ionic liquids, and what's the water efficiency?
The use of water in the original recovery, I use it for illustration purposes. That's how we actually discovered it, and that's not the way that you would do it. You would want to use a more volatile solvent. Ethanol has been proposed. The recovery aspect, I didn't mention this. The cellulose technology itself was licensed by BASF, and they are trying to develop a new cellulose fiber to replace viscose. And one of the key economics to that particular process is exactly this: what is going to be the efficiency of the recovery? The recovery can be very efficient, 99+% of both, but it also, if you do that, can be very energy intensive. So right now the research is how do you bring down the energy cost and therefore improve your economics for the whole process. We have been looking at different ways of coagulating this, subject of several patent applications that have gone out or are going out. But the bottom line is, from the chemistry works. The ionic liquid is stable. The anti-solvent is stable. If you're using pure cellulose, it's easy. Biorefinery is more difficult because you have so many products that you'll have to clean up. But even there, we'll call it a black oil just to give you an idea what it looks like. We've taken the black oil and used it to redissolve more, and it'll keep going. It could become saturated with certain constituents, but they don't keep it from doing the job of continuing to dissolve the biomass.
Hi there, my name's Austin from the University of Florida, and as you can imagine, the red jacket threw me off at first, but I was actually really impressed with...
My father graduated from the University of Florida.
Oh, well, there you go, SEC all the way. But I was really impressed with everything you had to say. I had a more broad question, however. Did you come across this through serendipity, or did you actually think through that using these liquid salts would actually have this effect and have these results?
We started working with ionic liquids on purpose in 1996. That was when I had come back to the university as a full professor. Went to a meeting and I'd heard about what they could do. We actually started in the field of separations. While we were working in separations, we were approached by an industrial contact who wanted us to decolorize Langostino shells, which was a separation. So we were going after the astaxanthine. What we found when we tried to decolorize them is we actually were dissolving portions of them. And of course, even back then, this is in the early 90s and late 90s, early 2000s, this idea of carbohydrate economy is not new. Those things were new. The principles of green chemistry, I think, were laid down in 98. And the idea of using renewables to develop these things. What I found funny is that once we did it, we had a hard time getting our industrial colleagues to patent it because they didn't understand the significance of what it meant if you could directly dissolve cellulose. And we finally convinced them, but they actually gave up on it and relicensed it back to the university, and then they did it at the wrong time because like a year later we licensed it to BASF. There's just a tremendous thing that you can do. I would say it's a luck. It was understanding what we wanted to do in the field of sustainability and being at the right place at the right time.
Last question.
What do you think about the dissolution of biomass in magnetic onic liquids?
All right, I didn't see who asked the question. Oh, in the back, okay. Ask again, please.
What do you think about the dissolution of biomass in magnetic onic liquids?
The question would be, I understand the question, actually, so it's a good one. The question would be why you would want to do that. First, the magnetic onic liquids are going to use probably a metal, and that means that you're going to create a bulk commodity that has a lot of, let's say, iron or something in it to make it magnetic. But the chemistry of this, which we might have to talk about offline, is that the anion is really responsible for getting in and doing the cellulose. So the only time that you would be able to use the magnetic property would be to recover the cation, perhaps in the coagulant. Magnetic field may or probably won't be enough to cause any coagulation in the solution, but of course you may be able to separate it from water, but the key will be dehydrating the anion, and you'll still have to do that even if you can get a bulk separation. Do you have some work in that area? I'd be interested to hear about it.
Yes.
Excellent.
Okay. Thank you, Robin.